Hello, 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 hello.
Testing 1, 2, 8. I am. All right. Welcome to the pre-show.
2 minutes. Oh my God. 1 minute and 10 seconds. Yeah.
Well, a foolish consistency is the hobgoblin of little minds. It says so. The Native American guy, you mean? All right. Let's put some polish into it here. Oh, you know, I was in the middle of saying a foolish consistency is the hobgoblin of little minds, and a foolish accuracy is expensive. That last digit of precision is really expensive, and we'll talk more about that in a minute after I tell you, Sam, stop talking. Thank you, Sam, for your patience with my inadequacies, my penchant for amusing myself. Oh, well, I guess it's last weekend was Women's Month. This month is Persnickety Jackass Month, and we've decided on the benefit of, after the benefit of counsel, to not have a featured speaker on that subject, because women in fourth were wonderful and are wonderful to this day, but persnickety jackasses in fourth are probably legally actionable. All right, welcome to the Silicon Valley Fourth Interest Group. I'm Kevin Appert. I'm your program chairman. This is the afternoon session for April. And it has come to my attention that some of you folks don't know what things are going to be where on this presentation. My advice is that if you're watching it live, you can go to Google and Google the sentence, when is the next SVFIG meeting? And Google, ever polite, will tell you a list of links. And one of them will be the speaker's schedule page. I'll leave it to you to find which one is which, but we recommend you click on github.io for the schedule page, GitHub, and that will be a list after all the random blather that has promulgated. It will be a list of what speakers we think will be presenting and when they will be presenting. The thing about this particular document is frozen at 4 o'clock in the afternoon on the day of the meeting. That means that when the meeting's over, we'll know who spoke when. Later on, after the talk is archived on YouTube, there are meeting notes. We're going to try to mark the YouTube page with a comment that says, go to this page for the meeting notes for all our meetings. And we're looking for a volunteer to make that inscription upon the YouTube page and see Dennis at the break or see me. Otherwise, I will mock you all and probably wind up doing it myself.
And I've already started the conversation in our mailing list.
Oh, that is 2 steps ahead of me. Dennis says he's started that conversation in the mailing list, for which I'm grateful. Does anyone have any announcements, rumors, gossip, slander, libel? Okay.
I'm trying to reintroduce the mother of all cliches. Oh yeah. It's been years since the Desert Shield. So it's time to reintroduce the mother of all cliches.
All right.
Because the mother of all bombs is in use. So it makes time.
Yeah, there was, I think, a comment in Hogan's Heroes many years ago where somebody said, you know, the code names for these projects, for these missions are getting better. And I think Colonel Hogan said, yeah, I think they got a Madison Avenue guy to start making them up for them.
And Kevin, if you search Da Vinci,
Yeah?
search Da Vinci,
And then what happens?
you'll see.
Do I have to know how to spell Da Vinci?
Da Vinci. No. Okay. Da Vinci space robot.
Oh, the medical thing. They're a fun bunch of guys, those Da Vinci guys.
Da Vinci robot. There you go.
My son used to harangue me because I would say it robot.
Yeah, and that's the picture. That's what was working on me a month ago.
And for those of you, that's what was working on Dennis,
Yeah.
our web broadcast YouTube meister and media guy who wasn't here last month. He
For a
was
good reason.
ably replaced by Brad, and we're grateful to Brad for stepping into the breach, and we're very grateful to Dennis for his continuing efforts to bring our meetings to the world. Thank you, Dennis.
And I thought you'd like to see the robot. I never saw it.
Yeah,
At the time.
as it turns out, there are, years ago, there was a screening, a prostate cancer screening. And after you got screened, you could go off to this other room where they had a demo Da Vinci all set up, and you could actually grab the controls and wiggle the arms around and put a rubber band on a polyp, and it was great fun.
Cool.
If you ever have the opportunity to play with one of these, I recommend it to you. It's an experience.
It removed a tumor, cancerous tumor from my kidney. I have 4 holes in my stomach. Those 4 arms you see on the robot.
It's not really a robot so much as a telemanipulator.
Yes. Master slave.
But we call them robots because we know that word.
Well, they are certainly drive-by, not wire. Well, drive-by wire is the term. I like Waldo.
Okay. So this is in the past now. April 17th through the 21st was femtosecond week. And I gather the ghost of Grace showed up with femtosecond long pieces of wire. I think, you know, what is it? 10 to the minus third feet. Or 10 to the minus.
A meter per nanosecond.
Or so. You know, there was a discussion. It's like, well, how long is a nanosecond long wire? And the answer is, yeah, it's about a foot. Well, how long is it exactly? Well, that's a hard question. And we were getting into propagation delay and all of the attendance. So speaking of time, which I was, it's time to ask again. Anybody got any rumors, gossip, slander, libel, announcements? Okay. I'd like to announce that next month's meeting will be a workshop for folks that are being introduced to the wonderful world of Fourth. We're hoping to suck some folks in at Maker Faire. So the main activity of this organization, if I may use that word incorrectly, is to go to Maker Faire. TIG has a booth. We're looking for volunteers. If you can't be here today, maybe you can be there today, in which case contact TIG or contact me, and I'll put you in touch with TIG. But the Saturday after Maker Faire, TIG will be running a workshop, and details for that will be on Meetup and on the schedule page when we know more. So, speaking of time, which I was a minute ago, this is a timeometer. And it's a pretty hefty, expensive, you can see that one in particular is $2,450 American. So you put your watch, your digital watch, your stopwatch. It could be an all-electronic LCD display stopwatch with no mechanical parts other than the buttons and switches. Or it could be an old mechanical Gruen or whatever with no electronics, no battery. You just wind the crown and it's happy. And it reads out how many seconds per day you are off. And it does that with pretty darn good accuracy. There are variants on this particular device that have hooked up to them a GPS time base where the clock accuracy is the clock accuracy of the GPS satellites, which is pretty darn good. I was thinking if you took a Arduino and some little sort of receiver, you might be able to build a little doohickey that would have a coil that you could sit your stopwatch on and read out the time. And then maybe you could buy one of these 1 megahertz cesium clocks, or sorry, 10 megahertz cesium clocks, or 10 megahertz GPS time bases off of eBay. Both of those things are available these days at remarkably reasonable prices. I mean, it always amazed me that you could get a cesium or rubidium beam standard off of eBay at, you know, pennies on the dollar. And that might be fun for somebody to do. So if anybody's interested in trying that, you can contact me at the email address on the schedule page about it.
A stupid question.
Yes?
Does this work on an LCD watch?
You have a radio emission out of the 22Apr2017 crystal oscillator built into the, and you measure the accuracy of, you could do it with a spectrum analyzer.
It's EMI.
It's exactly right.
And it has an acoustic pickup microphone.
It has a microphone for the mechanical watch.
That's my thing. That won't work. The microphone won't work.
No, they're actually in the little box on the left. I believe on this one, there are 3 different modes of sensing for the exterior time going by.
Then that might work.
And anyway, oh, let's see, did I have any more blather to blather?
How do you determine the accuracy of the timeout?
That's a good question. There is a, for this one, you build a little doohickey, or they may actually sell you one, where you capacitively couple your really good 1 second, 1 pulse per second time base, which in general is hooked up to the GPS satellites. There are these GPS time-based receivers, and all they do is put out maybe, almost always there's at least 10 megahertz, and many of them, if not most of them, put out a pulse per second as well. And you put that pulse per second into this thing, and it says, oh, that's accurate to 0.2 seconds per day. And you say, no, you're off by 0.2 seconds per day. And if that's not good enough for the customer, you might tweak that little doohickey a little bit to calibrate it and put it in the center of the specification rather than just saying you are within the specification. Crystal aging on one of these things, they're usually pretty good for a while. The crystals don't age that much compared to the accuracy of a wristwatch. Many years ago at NIST headquarters, they had an exhibit. I think it was the centennial of the Bureau of Standards / NIST. And they had basically one of these things, I think, and invited people to put their watches on. And they were frequently off by a second or two a day. I think that there's a distribution, but they were almost always fast. There were very few of them that were slow. So I guess there's a bias to be early rather than late for the watch manufacturers. Well, they want you there on time, damn it.
Early is never a problem.
All right. I wanted to comment about podcasts because I think it was Podcast Week, or they were running a deal on how do you listen to podcasts. I think you could probably figure that out for yourself. This is one I recommend. Generally, show business figures at least one musician lately. This was their farewell to Don Rickles. It's Gilbert Gottfried and another fellow, but he's the banner personality. Does anybody else here listen to podcasts at all? John Batchelor, George says. George, what does John Batchelor talk about?
John Batchelor has a talk show with guests. No calls, don't bother calling, but he has guests from around the world, think tank guys that you see sometimes when CNN gets lucky and getting an actual expert. These are the guys that John Batchelor has 5 nights a week, and then he does historical shit on the weekends.
Sounds like we've now reached the point where there'll be a short lull in the action. Do you got your thumb drive?
Yeah.
Thank you. We'll take this. I have to remember how this works. We're going to take a minute or two to get set up for the next speaker. So be patient with us. You hold this. You take that. Stick this in. Alrighty.
Hold on. This one, 04 dash.
Can I just move it on my hard drive?
No, just play it off of here.
Okay. I'm not sure this is going to work.
Oh,
Oh, that's interesting.
maximize.
No, this is a pointer. And the thing is that this, I've used it with this computer before. It's just, it was plugged into the other USB port.
No, I never had it do that much stuff.
Guess it's all your fault.
I just want to tell you, in case you haven't figured it out, these things do much better with regular rather than rechargeable batteries. That extra half a volt makes a big difference.
I think to use rechargeable batteries for that.
Well, I had.
I'm gonna just bomb out of this.
Now let's.
Got it. Okay, I'm ready. Hello, I'm Dave Jaffe, and oh hi, in past years, I've come across a lot of material in trade journals and on the internet that are interesting to me, and I thought if they're interesting to me, they may be interesting to you. And so this month is another one of those, and so it's been a long time. I found a couple great articles from magazines that talked all about single board computers and stuff. So I'm going to bring you a bunch of those. And I also found a bunch of personal computer ads from years and years ago that I think might be amusing to you. So as far as these hardware items, these are things that I just saw in the magazine and put the picture on the slide and put some specifications up, but I don't know anything more about the board at all. I haven't used it, so don't ask me any questions. On each slide, there's a link to the page that describes it a lot more. So if you have an interest, I will be posting these slides, and you can go through them and check on the boards that you want to get more information about. So there's two articles that a lot of this stuff is from, and here's an article that I think I have 2 or 3 boards from. Again, here's the link to the entire article, and the first item is this Diamond Systems PC104. Who even knew that PC104 was still around? Well, it is. Yeah, it is, and they've advanced. It's a stack, actually a stack set of boards that plug on top of one another, and this was done way before Arduino was doing this with Shields. So they've enhanced these boards with a couple stacking connectors and connectors that go on the side. This one is a CPU board that has VGA, HDMI, LCD, and is compatible with ISA and PCI. And there are serial ports, USB ports, Ethernet ports, SATA ports on it. And so I think the dimensions of these boards are about 4.5 inches square. So, basically that's a lot of stuff to put on a board. Yeah. I remember starting out with STD bus cards, and I think that sort of morphed into PC104 cards. So they're still around, and I think some of them are actually used in military applications. Here's another board from Diamond Systems. Memory slots. I think this can handle up this much memory. And so this is what's called a mini PCI. And then there's also a term called one bank that I haven't heard about before. So again, USB ports, lots of them, serial ports, lots of them. I'm not connectors all over the place. There's a bunch more boards from this article, very recent, by the same guy from Electronics Design. This is a PCI Express mini card that's apparently a bunch of serial ports. 2 serial ports at very high speeds. And this is way larger than real size. Okay. Here's a somewhat smaller card, again, with serial and I/O pins. And you notice the edge connector is the same as this one. Okay. And that's what makes up the mini PCI card. PCI Express. Okay. Okay. Here's another one. This one is A to D converters and D to A converters and I/O lines. Again, sort of the same bus configuration. I'm not sure if they make a backplane for this or it just fits into a PC. What?
PCI Express is the follow-on to PCI.
Okay.
It's a smaller connector because remember PCI was this bus board
Oh, okay.
connector. So now they went to a real dinky connector. And many computers that have PCI Express in them may have an external connector. Yes. That you can plug these into.
Mm-hmm. Okay.
That's about all I know.
Okay. Well, it obviously added to what I knew. So, I mean, I'm showing these things mainly as a way of stimulating some discussion and interest. So, so this is a ruggedized next unit of computing for industrial applications. $600. It has an Intel processor, memory, solid-state drive capability. Again, lots of USB, Ethernet, video, and an optional RS-232 port. So this is all.
What does
Yeah.
rig mean in this context? And you said next.
Yeah, that's Intel term.
Yeah, Nook is.
Nook, yeah.
And I suspect that's supposed to be rugged.
Oh, yeah. I'm sorry.
I feel slightly better at this. So
Sorry. At least I got some discussion going on this.
if you do a lot of this kind of work,
Yeah, no.
or nookery,
No. So
Network unit. It's basically
Next.
a network unit. It's a hub. So it's something that you run Linux on.
you can run other operating systems, and Intel and other people have these very compact boxes that sort of serve the same purpose for personal computers, but this one is a little bit more industrial because of the giant heat sink on it. I suspect there's no fan, and
Most of them have no fan.
they're made.
Industrial computers.
Yeah.
what do they call embedded Windows these days?
Industrial computer. They call it a Nook. Like this would run a server.
But what's the operating?
It can run whatever you want.
It depends on which one you want.
I don't want any of them.
On very small ones, they now have Windows Home.
So
Well,
was this
Windows
something that was
Basic.
once called Wince?
There's Windows CE.
No longer Windows CE. No, there's a very stripped down version of Windows.
I'm just trying to make a very small joke about it. You right, Wince.
No,
You've succeeded.
Let's
Windows
move on.
was around.
Yes, I know it was a real thing, but you wanted Wince, yes.
Verge was a real yellow soda.
Yes.
They called it Verge. You don't think a yellow soda is called Verge. Yes, very bad name.
Well, in Japan, they have a soft drink called Sweat. I've got the can. Anyway, so this is this shows how these PC 104 boards can stack together, and there's common connectors along one or more ends that provide a bus here, and it looks like this is an FPGA I/O board using this processor, and has memory and flash on it, and I/O interface FPGA, and there's Ethernet capability as well. So, and here's a daughter board on top of one of these cards. This may actually be the CPU. Okay. 16 cores. It says it's an Intel chip here.
Well, that's true. Well, still a 16-core Intel. That's a nice computer.
Yeah.
That's the good news. The bad news is they're all 88s.
That would be okay for me.
With those boards.
Yeah.
Well, now it depends on which course. Right, if it's an I-7, that's a nice thing. If it's an I-5,
Yeah. Yeah, it could be.
good.
I can't read it, so I couldn't tell you. But go to the link. There's a link.
Yeah, click on the link.
It's not doing it. Has Ethernet. Lots. Yeah. USB connectors for SATA, serial, GPIO. It looks like this is could be a single board embedded system computer, I guess. Next, Intel Atom. So I guess this is a series that can include that can use one of these processors. So there may be different versions of this that have these different processors in it. But now you see a different pin out here. Yeah. Yeah. It almost looks like a memory pinout, but they do a lot in moving this slot around. But the neat thing about this is that it's like has lots of accessories. You know, memory, Ethernet ports, USB, SATA ports, UARTs, sound and graphics support. So you'd have to plug this into some kind of bus that has all these connectors. Yeah.
There are no connectors on this board.
Yeah, except that one, right? Yeah. Yeah, so I remember back in the day, they used to have basically an XT computer on a board about this size. Yeah.
Little board.
No, I had one of those, but it was something a little different. Okay. Sort of along the same lines, there's this card. Yeah. So there's apparently different boards with different CPUs on them, and different memory options and display. What?
It's beyond the scope of this talk.
Yeah.
It's an ARM core.
Yeah, it's an
ARM core.
Is that 1 or 2 core?
A 6, I'm not sure.
Yeah,
It's an M6.
okay, all right, that's.
I'm not sure how many cores are on an M6.
6.
Maybe 6.
No.
No? M6.
Numbers don't mean that.
I was hopeful.
I'm sorry.
Okay. Okay, Raspberry Pi, Gumstick Pi Compute Development Board. So, so here's a board, plugged into a motherboard with all the connectors on it, and it's really cheap depending on what options you get. So, yeah, so that's really nice based upon this is a processor I never heard of. So.
That's another ARM core.
Is it? Okay.
Is that the Pi 2 or
Pi 3?
Pi 3.
Pi 3?
Okay. So there's a price for the development board and a price for the Gumstick part of it. Okay. Looks like this is another stackable computer setup here. I'm not sure what the Jetson TX1 and TX2 are. Does anybody know? No? So this is for drone and real-time video applications. So there may be actually a camera that you plug in here or on the bottom. So there's an ARM processor in it and graphics processor, lots of USB. Why would you need that much stuff on a drone? I don't know.
Drones are exceedingly computational intensive.
Oh, yes.
Okay.
Yeah, they're probably the worst road.
Okay. Well, that's why they have the GPU on here. But the interesting thing is they have all these accelerometer, gyro, and compass, and barometer on it. That makes sense for being a drone.
Yep.
It's so much cheaper and more power efficient than the terrain following radar. The radar altimeter, which, by the way, doesn't work during inverted flight.
Yeah. Yeah, I wonder what it says. Okay. So this is a 3D printer that does multi-layer PC boards. No limit on the number of layers. A 10-layer board takes hours to print, and apparently it does both the conductive and non-conductive parts as well. Yeah, so I thought that was sort of interesting. I hope it does bigger boards than this, but it looks like it works with normal files. And that was neat. Okay, this is a board that is actually a part of the Altera University program that you can get for $175 if you're involved with a university. And they actually wanted to give one to me. This was at a event I was at last week. So there's an Altera FPGA on here. There's a development kit. There's all sorts of I/O stuff and buttons and switches and 7-segment LEDs and USB and a bunch of connectors over here. And they had this to show this off. I guess some students did a Rubik's Cube robotic solving deal with servo motors and stuff. Well, they recreated this at this event I was at, and it did a pretty damn good job in solving the problem. So it had, there was four servo motors, and they one of these connectors hooked up to a camera, so they lit. So the camera saw one side of the Rubik's Cube and would rotate the Rubik's Cube around to see what all the sides were, and then it would go to work in solving this. So that was a very good demo of the work. And going from the other, so here's a picture of how the setup is, and these are servo motors here, and the camera, there's a ring light down here and a camera below that looking up. This is able to rotate the cube, and then the other two on this side can deal with one slab of one side of the Rubik's Cube. But not to be outdone, University of Michigan has just installed this very large functional Rubik's Cube on campus. And it's supposed to be the largest solvable Rubik's Cube, but it's not hooked up to a robot or anything to solve it. You got to do it manually.
It's not solving it.
Yeah, it's not solved. Well, it's solvable because all the things move in the correct way. So, yeah. So there's video of these two linked here. So this is an Intel board called a Tiny Tile, and this is it. And again, it's very, very small, pretty cheap, lots of memory on it, Bluetooth, accelerometer and gyro. And there's also, I'm not sure what the Arduino model.
What's not on the lower right?
Yeah, okay, so there's one, I guess there's one that plugs into an Arduino. Yeah. Yeah, this looks like an HDMI connector.
That's the one you posted to the email list.
Yes, it was. Yeah.
Size-wise, I'll bet that's USB.
Oh, it's
That's,
3.1, version 3.1 or something.
no, that's not C. That's still the asymmetrical.
Oh, okay, just in a weird location.
That's one I have.
Okay. And comments?
Comments, I'll be happy to demo it next month if I can schedule the time. Well, because we've got a camping trip.
Okay.
Yeah, this is the board that I'm currently using to work on the Kestrel project. It is the only board that I've successfully raised external static RAM on. This is one of the boards that failed for me trying to raise it by way of USB, because there's a separate USB board that you can use to program it. But on the other side of that is a PIO connector for a Raspberry Pi. So I was like, let me just get the Raspberry Pi and program it that way. Worked out of the box. It's like a Macintosh for FPGAs.
Are you available in June?
Possibly, maybe.
There's no meeting in May.
Oh,
There's
okay.
a workshop and a maker fair.
Yeah, so yeah, maybe in June I'll give a demo.
Okay. Thanks, Sam.
Sheer $100 So the little white strips, all total, is about 96 pins of I/O, and then you have another 4x13 array of I/O pins there, and then the 4 PMOS are another 32 bits of I/O. This thing releases probably close to 200 I/O.
200 I/O lines. Yeah. The black ice board is in process. It seems from the website.
So this is I have one of these as well.
Yeah.
I have not been able to raise this except to flash the ARM chip that's built into it. But I figured once I get the IO board working, then I will turn my attention to my Storm Black Ice and try to get that working. But it's the same sort of deal where, you know, it's targeting the same audience as IO board, basically.
Okay.
Yeah, that's Ken Oaks.
Yeah, I think I picked up these links from like 2 months ago. The microchip 18 mega 168 controller and debugger integrates with Atmel Studio for programming, virtual COM port, USB powered. Looks like, again, a lot of connectors or places for connectors here. And this is the active part over here, it looks like. Okay. Oh, this is really interesting. This board supports light cubes, so you can have a 5x5x5 RGB light cube made with this board, and it has a light sensor for dimming, Bluetooth control, UART and stuff like that. So this is the board, the hardware used to build up a light cube. That's pretty interesting. Here's a single board computer system. Looks like it could be rack mounted. Yeah. Curiosity board from Microchip. Integrated floating point unit, Wi-Fi module, GPIO, Bluetooth stereo. And then these sockets are for there's a bunch of adapter boards from this company that you can plug in here. Okay, this looks like the Wi-Fi board. Okay. And now we come to some personal computer ads. So there was 2 articles I pulled this out of. So this should bring back memories for some of you. 80 megabytes for under $12,000. And they don't fit in your pocket though. From Sunnyvale, California. What the heck is electronic mail? From Honeywell. Not sure what year this is, but interesting. He doesn't have a computer on his desk. Yeah. Versatile, dependable, compatible, maybe even sexy. Yeah, you got 1200 baud modems and up to 4800 baud modems. I remember that. WordStar, an ad for WordStar. Who used WordStar?
That looks like the front business end of an ADM 3A
Yeah.
terminal of dudes.
Yeah.
That's an ad of three.
Yeah.
Or wannabe.
But they're not even showing WordStar on the screen.
What's the point of showing the terminal?
Yeah. 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 I don't get it. Do you have cobalitis?
Cobalitis.
You can learn about this is an ad for COBOL books
Yeah.
for students, written by Edward Yurden. Okay.
Old memories.
Yeah. So this is for the DEC System 10. They're calling it a personal mainframe.
Personal.
Mainframe.
Yeah.
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 And it runs COBOL
Yes, it does.
and Fortran.
Well, up until fairly recently, you could make a good living coding COBOL.
Yeah.
And it had not so much for.
So I think is this it behind here? These racks?
Yeah, that's a top 10. Maybe.
Yeah, because I didn't, I was looking for a picture of it,
That may be a monitor suite. Yeah, that's
It's got-
BT100.
Oh yeah, this is a BT100 here, and this is a line printer.
But that's a top 10 box behind him.
Yeah.
The boxes. Some of it's
So-
space.
Yeah, 512 users. Nice. Here you go. Briefcase portability. You got your keyboard and modem and display here. You're all set.
Just need to have a phone to it.
Yeah, so it's not a computer. It's just a terminal and
It's just a
keyboard.
terminal.
yeah.
It's just-
Acoustic coupler. Okay.
Oh.
Yeah. So the point of this is that you can use these type balls for any language. There's a optical page reader version that you can type in so that other people can read it. I mean, so that can be read by optical page reader. And, okay, here we go. An NEC laptop. Clock speed 9.54 or 4.77 megahertz. Yeah. Yeah. So the interesting thing about these early LCD laptops is that they had very low contrast. And I had one around this time frame that you could barely see. Yeah. Yeah.
That's why you needed the grid with the plasma display.
Yeah, I had one of those too. Yeah. Here we go. We got Elvira advertising. What is this? A database software? I don't know.
It doesn't matter.
It doesn't matter what you do. Okay. Here you go. The hard disk you're waiting for. 10 megabytes for $3,400.
That's a lot of space.
Yeah. Yeah.
What's the Fujitsu Eagle?
Oh, here's that same ad again to compare. Seagate 80 megabyte drive, 5 1/4 full height. Yeah. Hey, look at the mechanism for the heads. It's huge.
It's terrible. They had to hunt whales to lubricate those.
Yeah. 10 megabyte hard drive, $3,500. 10 megabyte, $3,700 for Moral Designs. Oh yeah, Kromenko. Yeah. Oh, these were really neat floppy disk drives because they had a motorized eject mechanism on there. That was way cool. Yeah, the 8-inch ones. Yeah, that was really neat. Yeah.
Right here from Stanford campus. Was Carruthers Memorial Hall.
Oh, yeah, and that's still around. Okay, I forgot about that. Lotus. Okay, Lotus one.
What was that?
It's a database system, right?
Magellan was
Yeah, I think so.
a spreadsheet database?
Oh, Magellan will search your entire hard disk and come back with a list of relevant files in seconds. Yeah. Utility function, copy, delete, move, sort, backup, rename groups of files to your entire directory. Yeah.
Magellan exploring the universe.
Yeah. Shugart disk drives. Yeah. Well, this is a much older ad, obviously.
Yeah, we went back a decade.
Yeah, yeah.
Operations in real time. I think was the thing it had to be within like what 5 seconds.
Yeah.
I think there's at least one episode of like What's My Line on YouTube that you can see ads for Remington Rand
Yeah,
computers.
I remember that.
Back in the days when they had
Yeah, they
bituminous coal that they were shoveling into them.
When the studio used the jackets and ties.
Yeah.
Well, yeah. What else would one wear?
It's not television after all.
Here's an original Apple One ad. Yeah. Includes 4K bytes. Yeah. Tape. Apple Basic is free. Wow, that was a big deal. Apple II, right? Yeah. Yeah, this is a big deal. This TMS 9900 was, a 16-bit computer, and that was a big deal, in the 8-bit days.
Yeah, it's the very first 16-bit check.
Yeah.
60.
Right, because they actually had one board that had the whole thing on it.
Was it common package for the 99?
4800 baud digital cassette. That was actually pretty fast. S100 card. Those were the days. Yeah.
The last one we saw with the cassette storage, they used to have a Trash 80 with an extra stringy floppy.
Oh, a stringy floppy.
Yeah, and TI, I think came up with the color. Tandy and TI, I think kind of colored.
Yeah.
They used a stringy floppy in a short time.
Yeah. Okay.
And then of course all this was
Yep.
Back in the day when nerds thought they were sexy. I think Exitron is still around.
data.
Yeah.
I have a friend who just got hired there.
Oh, good.
George Morrow's sticker things. I love that.
Yeah. So,
They manufacture Apple, yeah,
so these were more S100 boards and 16K static RAM boards. That was neat. And you configured the address space with these dip switches. I remember doing that.
Yeah, George Morrow used to be on TV every so often.
Yep. Extensys. I think this is another. Yeah, this is another S100 bus computer company.
In Saratoga, is that where it's addressed?
Sunnyvale.
Sunnyvale.
Yeah. So one of the neat things about these S100 boards is they had the power supply was like 8 volts DC, and on each board you'd have a regulator to regulate it down to 5 volts. And depending on how much you were running on the board, you know, these things got pretty hot. And I remember during the winter, it actually provided heat for the computer room. Great heaters. Lotus 123, I never got into that at all. And here,
2 volts is 4 watts.
yeah, we got Victor Borga and Verbatim. Floppy disk 8-inch with ads. Sony came out with a 3.5-inch disc, and I guess it was started with Apple, and then PCs had it. So that, you know, if you had a PC, you had to deal with 8-inch floppy disks of different density, different size, different sides. Some of them were double-sided, some of them weren't. And single-sided, double-sided. Some of them, you know, like the first 2 tracks might be single density and the rest double density. So it's just varied all over the place. And then there was, you know, 5 1/4, and there's some with 48 tracks and others with 96 tracks, and then you had the 3.5-inch discs, and they were 800 megabyte, 800, 720, and port 4, right? Yeah, yeah. So there's a lot to deal with. So I remember I had a procedure if I wanted to get somebody with a different computer, you know, going with software. I wrote a bunch of programs that allowed serial transfer, you know, into the operating system. And so it would take about an hour to figure out how to program the serial board on the other computer, and then download no, well, I was using another program before Kermit, but you had to download the companion receiving program into the other machine, basically by pipping it into memory and then saving it, and then editing the ASM version and changing the ports and stuff like that to make it work automatically. But you know, I did a lot of conversion to a lot of different machines, so that was fun. Logitech mouse. Yeah, boy, they were around back then. Yeah. Yeah, here's a two button mouse. It's the new standard. No, this wasn't the one for the Apple.
No, this Microsoft's here, the original Microsoft first mouse.
Yeah, right.
Total disaster.
Yeah. Do you remember the mice that you had run on a board that had blue lines one way and red lines the other way, and it would count the number of lines? Yeah, I had. Yeah, optical, right. And then you'd really mess up somebody if you turned it 90 degrees. They tried to use it. That's fun. Ah, ZX80. Yeah. Fun stuff. Apple IIc. That was really nice. I never had one of those. Apple II. Wonder who the ad guys were. This. It's a color computer with a built-in cassette. Built-in cassette.
Joysticks?
Yeah, maybe it was a game computer too.
It's gotta be. Yeah, it's a game console that you drop into the keyboard. Yeah, disk or tape drive.
Built-in sound synthesizer, 2 game controllers, joysticks.
All you want to do is play games.
Yeah. So 14K basic in ROM.
All you can do is basic.
Yeah. Apple II again. And what version? What Apple was this one? Apple III. Yeah, didn't see a lot of these around. Solid computer, yeah, that's another S100 computer. Yeah, that was good stuff. Yeah, VIC-20, yeah, that was nice. Built-in BASIC and stuff.
Very young William Shatner.
Very, very young, yeah. Look at that.
Wow. Very young.
Oh, here's the Osborne. Yeah, $1,800. Yeah, including software. Oh, and yeah, I remember this, the 5110s. Yeah, I like those a lot. That came out a little bit before the Altair and stuff, but it was really neat because it had a nice CRT display here. There was a tape drive, an optional tape drive, and the thing that really got me is there was a switch, APL and BASIC, so you can run both of those just by flipping a switch. Yeah, so that was neat. TRS-80, and this is the Model 100. Yeah, that was a very popular machine because even because it had a limited display, but it had a built-in modem. So a lot of like news reporters used these and would modem their stories in. Yeah, I had the NEC version of this. Yeah. No, this. Yeah, it was. Yeah.
It basically just brought out the bus on the connector. Right. It's like a wire up connector.
Yeah, I don't remember having that capability on the NEC version.
Video display and disk storage.
Yeah, so it's yeah. Color terminal.
You have a lot more, Dave? Or?
No, I'm at the end.
All right.
Apple computer again.
Go to the end of it then.
Yeah, Commodore 64. Mac. Apple III. Apple III. Oh, I thought it was pretty clever. Your keyboard where you have the direction keys and you can use it like a joystick. And that's it.
Where's the digital group? No.
They didn't have pictures of that in there, so. Okay, but I would have included it. Yeah. Heathkit, I had a Heathkit.
All right, there'll be a short break.
Thank you very much.
He's supposed to be waiting. Yes.
Oh, where's the?
Yeah, I remember.
How do
The optical mouse on that pad.
how do I get the? I don't know. What's the icon? Where's the icon for ejecting the flash drive?
Oh, to unmount the flash drive?
Yeah.
Yeah, well, I guess you just go to the Explorer. You go to the file manager because it's a file device. And look for the volumes.
Got it.
All right.
I'm a Windows expert. I'm pretty good at Windows 98.
Yeah.
Service Pack 2. Second edition.
Okay. Uh-oh. Are you there? I can't hear anything. If there's any sound. Oh. Okay. Oh, I guess, can you hear me? Or something's lagging. Something's really lagging. Where's that? Oh, this is a different screen share. I still can't hear anything from your end. Hi, are you now seeing my screen share? Let's see, except I can't hear you. Is any, okay, so you got sign language. Is this, you're not seeing, I'm not seeing my screen share. It says I'm screen sharing, but I'm seeing you guys. Is it screen sharing? It says I'm screen sharing. It is. So if I do that, you're seeing that. And where I want to go, yeah, let me go over here to Fourth Cozy. You followed me? Why can't I hear anything? I need some feedback here. What's happening? Yeah, where I want to go. Hey, there it is. You followed me? Yeah. What's happening? Yeah, where I want to go. Hey, there it is. I'm echoing. Little picture I'd like to have. I'm not even saying anything. I'm in mute. Anybody see the screen? No.
Yeah, I know, I know what you're saying. Sometimes we have trouble with the mic, sometimes we have trouble with YouTube. Right now, have it going into the laptop, coming out to the Wi-Fi onto the little development board, on the next table. It's a good question. Come up with a good answer.
All sides.
Okay. Instead of having a regular meeting, which we don't do, it's going to have a workshop.
Don't hear anything from anybody, so I don't know what's going on, but if people can hear me, let's see. Oh, let me just go through. These are my notes for today. Even if this is Braille, as far as I know. One thing, I see that there's a lot of.
Can you hear me now?
Comparison. Let me get,
Can you hear me now?
I don't know what that's. Anyway, yeah, the interface here that is being used is this IUP, which is they're very big on Lua. Wanted to mention that from earlier. Wish I had feedback. Oh, in the David's talk, this is boy, it's weird not to, come on, what's happening here? I don't see anything going on.
Bob, I think we are getting feedback from your computer is coming through your mic.
So I'm seeing in any case, yes.
Do you have a headset?
Talking about some of these old computers, the Ampere here was, that was of the age, you had to have a bright light over the screen. But that was a pure APL computer. And then there's a compact suitcase, and here's a K-Pro 2000, and those are the, you can see the Cozy's always been oriented to be with you. But, you know, I see this coming up on my other screen here, but no sound. Hello, there's no sound.
Bob, we can hear you perfectly fine, but if I have the speaker on here, it has a feedback loop, just like the feedback loop that you have. Start your talk the way it is, and unless you can find a headset real quick, just start talking. Start your talk the way it is, and unless you can find a headset real quick, just start talking.
Oh, actually, I don't know what was, okay, sorry.
Start your talk the way it is, and unless you can find a headset real quick, just
Oh,
talking.
let me give, I don't know what was, okay, sorry.
The way it is, and unless you can find a headset real quick, just talking.
Oh, okay. Actually, it's the speaker back to me. Okay. Oh, okay. Actually, if I just mute my speaker, okay, I can't hear me, but I guess you can. So, we should be, yeah. So actually, if you can hear me, good. Okay, this is at least sign language. Yeah, damn. I don't know whether you've been following me. I've been going along here because as long as you can, see the damned cursor. Just going through this, if you didn't hear before, Lua, IUP is what this interface is. And it's definitely, the code is in the TUI script, but anyway, they're big. I'm control F9ing this. I'm just going to go ahead. But this is the interface
without you having a
it's
headset.
Brazilian, and they're very big on Lua.
We've got a huge loop
and
with
there is
you
a
talking.
bug in the interface with this, which is just not a high priority. Let me start. Oh, the one other point I'm going to throw in, because following David's talk, is definitely check out this page that has my old hardware. You need to, I think, start with an interface. I'm going to go through this in a somewhat different order with this. I'll go, well, I'm going to start, need to update on what's happening.
Unmute now. Bob, somehow you're muted and I can't unmute you. And if you turned off your speakers, that means that you don't hear this either. Bob, somehow you're muted and I can't unmute you.
say we're going to be back in 10 minutes with.
Bob, excuse me, Bob. It was there for a minute. You were unmuted for a moment. Excuse me, Bob. So, why don't we try this another time? This is just, it's not usable the way it is. It's not workable. It's not working. Why don't we try this another time? This is just, it's not usable the way it is. It's not workable. It's not working. Why don't we try this another time? This is just, it's not usable the way it is. It's not workable. It's not working. So Bob, I can't hear you if you're saying anything, and it's not working if you start talking. We'll go into an infinite loop. So Bob, I can't hear you if you're saying anything, and it's not working if you start talking. We'll go into an infinite loop. So Bob, I can't hear you if you're saying anything, and it's not working if you start talking. We'll go into an infinite loop. So,
Would it hurt your feelings if I turn the sound off? Because I don't want to listen to this.
Then let me just kill it. So, no, we don't want to leave. Stop presenting here. So I think what we've got to do
Testing, 1, 2, 3.
Say something.
The S16X4 instruction set architecture. Opcode map, instruction packing. Well,
I've got bars, so you should be coming out to the stream if it hasn't caught up yet.
okay. Cool. Okay, well,
Listen up, George.
George.
so this is kind of an impromptu talk. My name is Sam Falvo. I'm the guy behind the Kestrel project, and I've created a microprocessor instruction set architecture based on the Steamer 16 from probably back in the late 90s. And this served as the powerhouse behind the Kestrel 2 computer. As people probably may or may not be aware, the reason I stopped using this instruction set architecture and went with RISC-V is because I was running out of memory. The block RAM only gave me 48K of really usable memory. And unfortunately, the instruction density of this particular instruction set architecture wasn't all that compact. It actually competes with RISC as far as how dense it is. So what I ended up doing was for the Kestrel 3, besides making it an architecture with enough address bits that can support vastly more memory than just 64K of address space, it also preserved the instruction set density, because if I tried to just rebuild a MISC architecture for a wider data path, the instruction density actually dropped significantly, like right off a cliff. So let me start with a recap of the S16X4 family of CPUs, so to speak. This is the opcode map. And what we can see is basically the first 8, the first 8 instructions here correspond to the original Steamer 16 instruction set. And then I kind of added my own little stuff afterwards. This includes byte addressable memory, because before it was only word addressable. The ability to branch on a non-zero flag, which allowed me to implement the until construct in Forth, an unconditional jump, and 2 forms of subroutine calls. Now, as with all minimal instruction set computers, the instructions are packed multiple to a memory word. In my case, 4 instructions to a 16-bit quantity. The LI instruction here, that is your so-called load immediate. It's actually fetch from program memory. And that allows you to, for instance, load a literal 16-bit value pretty much as is. This, by the way, is the reason why instruction density is so poor, is because most of your constants don't need 16 bits. A lot of them actually need only support something like anywhere between 5 and 8 bits, typically. So that is why the instruction density is relatively poor with MISC. Another reason with this particular MISC architecture, why instruction set density is relatively poor, is that I did not have any return stack. So I have to juggle to and from memory a lot, and that means I have to push a lot of addresses onto the data stack. Also, the 3 deep stack really didn't allow me to do any stack permutations. So I couldn't do convenient things like dupe or over and stuff, which would allow me to reuse constants. Now, I did, as you can see here, I did expand the data stack depth an additional 3 registers with the 4A version of this processor. The intention for this, though, was to support interrupt capabilities. I never actually got around to doing that, but the registers are there. So it's just a hop, skip, and a jump away to support something like stack permutations and things. So here's an interesting conundrum. Now, I'm not necessarily going to do this for the Kestrel 3, except maybe as an I/O coprocessor, for example. But how do we expand its memory capacity? So if I were, let's put ourselves in Intel's position, for instance, and we want to market this product to, you know, a market segment that requires a lot more memory functionality. So how would we go about doing that? So some of the things that we would like to add in order to make this like a real fourth processor is we'd like to add a return stack. We'd like to add data stack manipulations. So right there we've got 4, 5, 6, 7, 8, 9 additional instructions. Keep that in mind. We need instructions to handle 32-bit and wider constants. And we need more convenient arithmetic and logic operations, things like inclusive OR, multi-bit shifts, an ordinary subtract operation, for example. So there are several methods that we can use to do this. And if you recall back in our opcode map, most of our opcode space is taken up. We don't really have all that much leeway as far as where to go. But we do have this empty segment here. We've got 2 free opcodes that we can use for whatever purposes necessary. So the first approach that we can take is probably the most obvious, and this is a prefix opcode. With a prefix opcode, we set internal state into the CPU where we maintain this hidden 5th bit, if you will, possibly even 6 bits. And these bits are fed directly into the instruction decoder itself. So as far as the instruction decoder is concerned, you're dealing with 5 or 6 bit wide opcodes, even though from memory you're only drawing 4 bits at a time. So with that, we can see here, so we've got a total of 16 usable instruction spaces here, and 2 of which we can use to switch between these different spaces. I'm sorry, 16 instructions per space, and we can select up to 3 spaces, 1 being the default, and we have 2 additional selectable by these prefixes. So that gives us a total space of 46 opcodes. Now, it turns out that you need maybe about 32 opcodes in order to form a really usable fourth processor. And even then, more often than not, you're dealing with like 29 to 30 or so opcodes. So we've got plenty of space if we wanted to take this approach. There are some caveats. One is if you implement this naively, all of your extended opcodes now take 2 cycles instead of just 1. If you're a little bit more clever, you can decode the 8 bits in parallel. But you have to remember that you need to shift your instruction register by 2 slots now instead of by 1. So now we're starting to get into some of the instruction alignment issues that you typically find in complex instruction set computers. But it's doable. At this scale, this is a very solvable problem. A second, perhaps more obvious approach is to just say, you know what, we're fourth engineers, we're just going to rewrite the whole damn thing from scratch and just come up with a brand new instruction set. And that's doable, but again, you want to preserve your previous investment. So what you do is you typically reserve 1 opcode as a special kind of jump. And this jump instruction takes as an address, a parameter, if you will, where to start executing code in the new instruction set. So not only does it transfer control, it simultaneously and atomically changes so that you have a different instruction set at your disposal. This is also quite doable, and being that this is a fourth-based instruction set, would be very small. but it's still not insignificant. So to give you an idea, the S16X4A is, with all 14 of its instructions implemented, close to 300 lines of Verilog code implemented. I have a prototype 64-bit MISC processor, which implements a lot more than just 16 instructions, but it comes in closer to 1,600 lines of code. This is still doable and understandable by a single person, but I'm going to argue that it's just barely so. It's right on the edge of what I'm happy with in terms of implementing this processor. I've seen other processors come in at smaller sizes, and I'd like to try and reduce that down if possible. So imagine a CPU then, if you're a commercial entity, lines of code isn't really a big thing. So for that, in that particular case, you can actually synthesize a processor with both of these execution units, if you will, in the same actual package, and you just ping pong between them. So presumably your S16X4A has a jump instruction that switches modes to S64X7, but then the S64X7 would presumably have a counter instruction to go back to the previous mode if you needed to. There is, of course, prior art to this. The Intel Itanium is probably the most famous one that comes to my mind. But in terms of more popular, commercially viable processors, probably ARM and the thumb instruction set is the biggest example. The next one that I'm familiar with that really doesn't require anything terribly exotic is explicitly set and reset mode bits. And again, it's the same idea as the instruction prefix, but now you're manually changing these bits instead of having them automatically updated as part of the instruction decode process. In this case, we have instructions that basically set and reset bits in the configuration register. And based on these particular mode bits, you can alter your instruction set however you want. There are prior art, of course, the 6502, which is an 8-bit CPU with 64K byte address space, was extended to be as proper 16-bit and later even 32-bit, although it never came to market, processor architecture, and it also had 16 megabyte address space capability without really changing the fundamental instructions too much. But it did that by way of exposing these mode bits. You do, however, want to be very careful with your mode bits, because in the case of Intel, they made a mistake with the 802.86 where you can turn on protected mode, but you can't turn it off. And that means if you wanted to multitask multiple MS-DOS applications on an 802.86, you basically have to reset the CPU and go through the cold boot cycle every single time it task switched back to real mode. That's one of the reasons why OS2 failed so miserably, is because when it tried to multitask DOS apps, its performance dropped off a cliff. So the final method that I wanted to discuss is actually MISC unique as far as I'm aware, and that is to have slot-sensitive instruction interpretations. So the example that I have is a jump opcode in, say, one of the later slots, and I will need to give a more precise example here so you can see what I'm talking about. Oops, I don't need all of that. So if we make this a go instruction, then everything from this point on is taken to be an address. If you make this a go instruction, then typically everything from here on out is taken to be an address, right? So you end up with these go instructions that have variable length addresses to them. That is a very typical MISC approach. I'm going to argue that a go instruction in slot 3 is probably not going to be terribly useful unless you're dealing with a very close, tight loop in a very precisely defined memory span. And similarly, a go instruction in that particular slot is going to be completely useless. It's basically going to be either a go to address 0 or a go to address -1, some other seemingly arbitrary architectural constraint. What this fourth method proposes is if we reuse the go opcode in slots 3 or 4, then we could have, you know, some extended function here and then some additional extended functionality there. This approach can be used to either set or reset these mode bits for explicit control. Alternatively, you can also use them as prefixes that apply to an entire slot. So the idea behind that is we might have a slot of normal instructions and then we have a different package of different instructions here. Right, so we can get by with 1, 2, 3 normal instructions, your normal typical MISC instructions, followed by a trailing go, which serves as a prefix, and then the next slot that's actually fetched, all of these 4 slots would correspond to extended functionality. So that's a possibility as well. More likely than not, if I were to do this, I would probably go with approach 1 because this is the most direct. Method 1 allows me access to 46 different opcodes, which is plenty for a minimal instruction set computer by far. All of these other approaches, if you look, for example, these explicit mode bits, this actually still requires that I add new instructions to get and set configuration registers, which are always good to have. Alternative instruction set, again, I need to add a new instruction to do that. The trick between these different approaches, of course, is can I add the minimal number of custom instructions and not run out of space in the process of doing it. So that's kind of the race that you're involved with this. So I have not actually implemented any of these so far. I'm actually kind of, like I said, I am kind of curious about implementing method 1 here. And the reason why is because I'm looking at the possibility of using or extending the S16 structure for the purposes of being an I/O coprocessor for the Kestrel 3. That is to say, I want to be able to offload I/O functionality from the host CPU. And in order to do that, since the host CPU has a 64-bit wide address bus, I of course need an I/O processor that can also address at least that amount of memory, at least the RAM space that's currently supported. So, and of course, making this and improving the code density is going to be a strong necessity as well. So that's why I wanted to add the return stack and the data stack and so on and so forth. So that's the rationale behind why I was looking into this. And method 1 is probably going to be the approach that I go. Yes?
On line 76, is that meant to be native or naive?
Naive, sorry. Yeah, but
It is naive?
it is supposed to be naive. I probably misspelled it, but
No, I thought it was naive. It requires extra flip-flops. So we got to have some other logic on board.
yes, so the naive implementation of this approach of using prefix opcodes, I would need to have at least 1 flip-flop for each additional mode bit that I support. And though the output of that flip-flop then feeds into the instruction decoder. And so I'll need those flip-flops, but I'll also need more lookup tables to implement, you know, the larger decode logic as well.
What's meant by naive implementation?
If you, perhaps it would be more accurate to say the most obvious, simplest implementation. So the idea is you execute these prefix opcodes as individual instructions unto themselves and not simply as modifiers for subsequent instructions. Whereas a little bit more clever is when you actually recognize in the instruction stream both the prefix and the subsequent instruction at the same time. This one would execute twice as fast, but it requires a lot more logic in the instruction decode path. Cool. Any other questions? Like I said, this is a very impromptu talk because I've been busy interviewing for a job, and hopefully by next week I'll know the results of that. So, yeah, the other thing that I noticed on the way here is I came up to the Bay Area in 2007, and that was the very first year that I attended SVFIG, and it's 2017 now. So probably around September or so, it's occurred to me that I've been part of this community for 10 years now. So just wanted to say thank you guys for having me. Cool. And that's the gist of my talk. Like I said, it's not terribly in-deep, or in-depth technical, super technical, but these are some of the different alternatives that I've evaluated, and I'll continue to evaluate going forward. Cool. Awesome. So I guess sweet. So we'll take a break, a short break for now, and I guess we'll be doing a talk with John Herbold.
Okay. Can you hear me now? I see that our audio-visual guy is having a problem counting, so he has to use his fingers. And am I, let's see, this, no, it says talk. You know, I have it on talk. Now, why you're not able to hear me, I don't know.
I can hear you. I'm looking at the YouTube live stream. Can you? Okay.
Good.
It's in the past. It does not matter.
All right.
I can hear you now. You're good to go. Like you start talking.
As if I had good sense. Okay.
There we go. Okay.
So we don't want that Wireshark.
Okay, yes, let us go unto the website called www.wireshark.org. There it is. This is a very, like I said, very useful. You can download, learn how to do it. It's got a bunch of documentation. You can even modify. You can add your own packet decoder if you want. Okay, this shows what Wireshark is all about. And here's some of its capabilities. And wow, you can even capture wireless. And not only that, you can also capture Bluetooth if you guys want to do Bluetooth devices. It'll do USB, it'll do Ethernet and wireless.
How about
CAN. Hey, that would be a nice thing to do. I bet you that can be added too. Okay. Oh, and if you want to get a degree in Wireshark, there is the Wireshark University. And I don't know if anybody wants to attend that. Anyway, so there's a whole lot of stuff here. But so the name of the website is wireshark.org. And you can get documentation, the latest Wireshark, you can complain about it, and do whatever you want. Okay? So now we're going to fire this guy off. As you can see, that's the name of the thing. Oh, yeah, and this will run not only under Linux, but it'll also run under Windows. So, and I'm running under Linux, so this is how I started. And in my case, I have to run it using as root. And put it back. There we go. There it loads up all the different protocols. Oh, that's an interesting thing here. Let's see. Oh no, I'm sorry. This filter, because let me pick the wireless. This is the wireless interface. As you can see, I'm just getting a flood of stuff.
There's a lot of activity right now.
Right. Okay. And as you can see, that's real time. Yeah. Yeah. You can see there's DNS, TCP, and a whole lot of other things. And you might want to. Yeah. Yes. In fact, if you want, you can filter by saying which thing you want to look at. Say we only want to look at TCP packets. Well, you hit this thing called expression. This window will pop up. You look for TCP, which starts with a T. And there we go. And what you do is you select one of these guys. Well, in this case, I'm going to cancel this and just put TCP. And then say there. And this now shows just all the TCP packets that I received. I can then change that and say, look at DNS. And I can see all the DNS packets. So it's a very useful tool, not only for networking and things like that, but like I said, you can look at your protocol between you and the USB device in question.
Is that wires?
Oh, this is what, no, yeah, let me show you here. This selection here, this shows all the interfaces that Wireshark will handle. As you can see, I currently have my wireless up here, but oh yeah, sniffing everything. Yeah, in this case, yes, exactly. Now that VIR is a virtual bridge because I do virtualization, and I can see what the traffic there is. ENS3 is my Ethernet port. I also have, you can see I have a Bluetooth thing, and I've got a whole bunch of USB interfaces. And you can see that there's been a lot of traffic here. That's probably the mouse that I've been using. So I think right now what we're going to concentrate on is the USB. And so I'm going to clear that guy. I believe this is the one I want. I'm going to be plugging in a USB disk. All right, here we go. And nothing's happening. I think you're absolutely right. Okay, let's see what. Oh, right. Oh, thank God. Good. Okay, let's try that again. Yes, we do. And let's start it. Okay, you gotta really stay on top of stuff here. Okay, let's plug this guy back in. Look at that. That is mass storage, righto. Okay, I'm gonna stop the capture so we can look at some of the stuff that comes out. And we can see there's these things like get status requests that come from the host. It sends a request down to the device. The device comes back and says, here is the response. Now you can look at it. There's three areas here. Here's the network traffic. The second one here is the actual interpretation. And the bottom one here is just the actual data. So you can actually go in and say, okay, what are all these things here mean? You just, yeah, you can shake it, to open it up. You look at all the different fields. And let's see what we got. Oh, there's all sorts of neat little stuff here. Okay, and this shows this right here, this blue. This is the response to request number one. It's just a, you know, client server type stuff here. So let's see. These are these are different requests. If you look at the USB, yeah.
What's the bar graph in the upper?
Oh, that right there. I should get rid of that, but I forgot how to do that. That's just showing what my graphics are doing. This is an old laptop from 2008 that I was able to abscond from a place where I used to work that threw this out. And it's unbelievable. It has 2 cores in it. Yes. I was walking around thinking I was so cool until I realized that modern laptops have got, what, 16 cores in them now? Anyway. Oh, yeah, right. So here we can actually go in and see what all the different commands are. Things, let's see. Let's look at this get status because it seems to appear a lot. Huh. Okay. Anyway, you can see there's a clear feature thing here. Does another get status, gets a descriptor. Let's see. And okay, this is cool. Yeah. So you can see if you need to look at what your traffic is, here it is. As we get down further, wait a minute. Like this guy right here, set address. That's one of the things USB does is it will, it's called enumeration. And this is what it does is the host is saying, okay, I'm going to set you your address. And as you can see, let's see, setup. Let's see what that says. Yeah, set address. Okay. And this is right here, you can see here, this is device 11. And then the response says, yeah, cool. Everything's good there. Now, this thing does a lot of get descriptors, meaning, oh boy, oh yes, this is saying like what language are you? And this thing will say, oh, this tells, yeah, this is asking actually not what language, but what are you? In this case, it's saying, oh, my company is Seagate, and I'm a backup plus slim, you know, basically a hard disk. And you got another one here. Let's make a little more room.
And where is that located?
What, the
Seagate?
right here. I just plugged it in.
But it's monitoring other USB things you've got going on.
Other things, I've got a USB mouse. Let's see, I think there's also a camera on here, but I've covered that up. Actually, I turned it off because I wanted to keep the traffic to a minimum. And this response here will say, oh, unknown data. Cool. This is another silly thing. Oh, request type. Oh, that tells the direction. Okay. Oh, it's got more crap in there. Anyway, but this is the kind of stuff you can see. There's a whole lot of stuff now. We have a bulk. That's the actual data. There are 4 endpoints. You have a control endpoint. There's a bulk in, a bulk out, and an interrupt thing. In fact, there was an interrupt thing. Now, this is making a request for data. And then it says, okay, here's what we got. Now, okay, this is, oh, crap. What is this? Yes, this is the stuff. Mass storage device. See, this is how the USB has to identify itself. In this case, it's a mass storage device, and it's a Seagate hard drive. And what the hell is this? I don't know. We got more of this crap. And there's all sorts of fun stuff. Okay, what I'm going to do is I'm going to unplug the disk here. And then I'm going to plug in some headphones. Wait a minute. And as you can see, we're getting a whole lot more traffic, but the stuff up front is used to identify what type of device. And then once that's all taken care of, I think if I turn on the headphones, then it will actually just start spewing data.
So this is really just a monitor. You can't go in and mess with the bits.
No, this is just a monitoring thing. If you're going to mess with the bits,
Like the network analyzer.
no, yeah.
Like, can you screw up and accidentally go in and try to do something?
No, this is read only. But this is, like I said, it's a good thing, especially if you're trying to debug your USB device. So let's see. Oh, we have a suspend here. Okay, cool. Okay, now I think if I do some settings here, sound, where is sound? Sound. Multimedia, there we go. Let's see. I think that's it. Yeah. Oh, let's try this. Huh. Wow. I guess that's all the things. Now, you understand what I'm saying is this is a very useful device, this Wireshark, so that you, if you want to debug your stuff, you want to see what's going between your host and your device. Now, again, that's why I wanted to be able to get G-Forth working under an RTOS so I can do my own USB devices. And I can use this to see what kind of traffic is going back and forth. Because remember, USB, let's see, it also has something called isochronous, which in this case, that's what this is used for, audio or video. You know, you can hook up a USB monitor if you want, and then you can actually see what the traffic is going back and forth. Yeah.
Isochronous meaning not synchronous.
No, continuous means what you can do is USB allows you to take some of the bandwidth of the USB bus and use it to do whether periodic input or output. You know, so if you have a speaker, well, you can periodically send data blocks out to your speaker so that you can play music. And you can assign how much of the bandwidth that you're going to use that will periodically go out to your device. Okay.
This is really software. The dongles were an add-on thing, and that gives you the ability to do what? Look at external stuff.
Yes. Oh yeah. I mean, look what. Yeah. If you want to see what kind of traffic is going between, you know, you and whatever you've plugged in. Yeah. This is a nice piece of equipment to use. And the important thing is, up here at the beginning is this stuff, this get status, because that's what the initialization, that's what USB does for initialization. In this case, it's doing a request to get status, and the return that you get is, in this case, oh, you see all these things right here, the port power? This shows, yes, this USB device has powered up. And then the next thing it asks is, this tells you what port it is. And it's giving you the same old crap again. Oh, wow. I didn't know that I did that kind of stuff. Okay, let's see what some of these other requests are. Okay, get status again. And in this case, still getting the same old stuff. Let's see if we can get something a little more interesting here. Okay, this clear feature. Okay, so this looks like it's going to unsuspend the port, and it does. Oh, here we go. This get status showed some differences. Here it shows here that the device is connected, it's enabled, it's got power, and it's high speed. Yes. So, what? No. This is only it's like a network analyzer. All you can do is just look at the data. If you're going to want to toggle any of that stuff, you're going to have to do it in your device. This is like a network analyzer. In fact, that's what you can also look at if you're want to debug any networking problems you're having. You just want to see what, yeah, you want to see what's the traffic going back and forth. I've done this where I found out that a firewall was blocking me, and I was able, when I turned the firewall off, oh, guess what? Everything starts working. So like I said, this is a very powerful tool to have, but you have to remember, Wireshark eats up a lot of resources.
I have UVerse TV, and I have it in a remote part of the house as well, and it's wireless.
Yes.
Sometimes it works, sometimes it doesn't work.
You can use this to actually look at that traffic. In fact, you can set it up so that you could show just that traffic. Because you remember when I turned on the wireless and we looked at for what's going on in Stanford?
Right.
There's a whole ton of it. And then I can say, no, I just want to look at what's going between this device and this device. You can do that, and that's what you could probably do.
Does it do measurement of rates?
Oh, yes. Oh, yes, yes. We have, let's see, IO graph, like right here. This is showing, I only turned it on. In fact, let me show, stop. Let me show the wireless stuff. Wow, a lot of Google stuff going on there. What's Google Cast? Anybody? Oh, Chromecast, that kind of stuff? Oh, okay. Let's see, what are we looking at here? Yeah, you can see there's a whole ton of stuff going on here.
Oh, you're playing with the guy.
Yeah.
What's your IP address?
Okay, now come here to statistics, look at the IO graph, and lo and behold, there it is. Nice thing about it is, if you want to look at a much finer rate, you can see things like this. So I'm not doing too bad.
Do they still have the option where you can see like images and stuff go by and it's only perfect traffic?
You can do that if you have a, I forgot what it's called, but you can write your own filter that you can interpret what's in that packet. So if you wanted to, you can say, oh, well, this is an actual image. Well, let me plop that up on the screen, see what we've got. Yes.
Wireshark has been around a long time, so the plug-in architecture.
That's it. It's a plug-in architecture.
Very robust.
Yes. And I've written 2 of these guys just to interpret this stuff. But it's very, very powerful. And like I said, you can do just about anything you want. But you're going to have to literally have either your own laptop or your own desktop, because this guy eats up a lot of processing time. I'm running under Linux, so I'm not doing a whole lot. But places I've worked, networking companies I've been at, actually do that where they want to show traffic between boxes. They literally have one, their own dedicated Wireshark device looking at that traffic just between the two boxes. And you can, like I said, you can find bottlenecks, you know, you can not only do debugging, but you can also do performance analysis to see what's going on. It's like what we have here.
You can also have it as an independent box, look at the traffic and say, oh, the server went to sleep.
Exactly.
So got any traffic.
Yes. And also know,
You can buy, and we'll start calling people.
yes. Yes, there are also the more unethical types in the networking world use Wireshark if they want to bust into a network. So you see, that's what I'm saying. You see everything. So you have to have good knowledge of networking, you know. Oh yeah, in fact, there's nothing. If you want to decrypt, you come in with your actually what you have to do is record a lot of these packets, look at the data, and then come up with a decrypting algorithm that looks at the stuff.
So you got about 15 minutes left. Do you want to talk about your project?
Oh, I got my other project, getting G4 to run into an RTOS. I tried using RTEMS. The problem is RTEMS doesn't support thread local storage for x86. The reason is G4 does rely on it. Okay, so I went, well, crap. So I looked at another one called, in fact, let me bring that website up. Uh-oh, what happened?
You're off. Try again. More than 4 hours ago. Try again.
Try again, okay.
You might want to stop our show.
Yeah. Thank you, okay, good.
You're on again.
Okay, NetX.
NSA sponsored search engine. It doesn't track you advertising.
Yes, DuckDuckGo, use that. This guy right here, this one has thread local storage. But it also, one of the things I'm also looking for is one that has its own shell, so that when I boot it up, I get a prompt and says, what do you want to do? And in this case, I want to be able to compile G4 in this case, as a NetX executable and say, go. The problem is the shell doesn't work. Yeah, and I now, you know, between looking for work and, you know, all that other crap, I've got to get into the mailing list and say, hey, why doesn't the shell work? In fact, here's some of the nice things about it here. It even supports symmetric multiprocessing. So if you've got multiple cores, cool. Here we go. This is the biggie right here. When I saw this, I cried. Thread local storage. And here's all the supported platforms. It's got ARM, Intel. This is a good one right here. Actually, this is not x86, it's 486. But you've got MIPS and RISC and Extensa. Oh, here's a complete list. This is really nice. So I'm going, oh, this is good. Now, if I could just get the shell to work and know that I can do that, then I can recompile G4 for this guy, and it should just work. Now, here's the thing. Look at this. Look at this. This is amazing.
Well, they got the wildfire package, but not the whole fire.
Where? Okay, got ARM. Here we got STM. Wait a minute. NXP bought Freescale, but who bought NXP? Qualcomm. Oh, yes. Oh, yes. Also, they have a NetX simulator, which is written using P threads, okay? All right, you got microchips stuff here, Zilog, so trust me, this is very powerful. It really made me feel good to see that. Plus, it's got, look at this, file systems, okay? It's got the FAT, so, you know, you guys want to have a, what do you call them? In fact, let me do this. Let me 86 this guy. Okay, let's get back to here. And yeah, you get FAT. Look at that. So all your Windows disks you want to look at, it does NFS. If you are manly enough to try it, you know, ROMFS. I mean, God, look at that. Device drivers. This is nice. It even has a cryptographic subsystem. Audio does graphics, right? Yeah. It used to have the C and C plus libraries, plus libraries. What's nice about that? GForth will let you access through the loader to be able to use library functions out of the C runtime library. Networking. Oh, this looks good. IP version 4 and version 6. TCP, UDP. Tang. Look at that. Yeah, streams. Oh, look at that. DNS. Oh my God. DHCP. Oh, flash memory. Oh, and this is the one right here. USB support. Both, because what's important is what I want to do is build my own hub. It'll be a super hub, meaning I'll have GForth running in it, and I can just develop to my heart's content, which also means with USB host support is I can plug devices in and fiddle with them. It also does device support, which means I can create my own USB device if I wanted. Okay, look at this, graphic support, frame buffer, all this nice stuff. Oh, and the nice thing about GForth, it has its own GUI, like, you know, Windows. So you can create your, you know, Xorg. Oh, this nutshell, this is the one I'm talking about. This guy, it won't work. And here's neat. You guys remember Pascal. How many of you ever did Pascal as a production language? Look at that. See, 1, 2. Oh, yeah, I couldn't believe it. Oregon Software, I remember, had a Pascal compiler. Amazing. And like I said, it's got a whole ton of apps, which means the nice thing about it, you can do, what I want to be able to do is write applications in Forth. You know, so this looks good. Oh, here, look at that. NetX Window Manager. Oh my God. This is
All this is free.
this is free, yes.
So how, why, what? Why are these people starting to do? Why haven't they imploded?
That comes about because
What do they sell them?
they don't sell. This is free. Well, I think what they do is it's like a company will say, hey, we want to use your operating system, but we need help, we need support. And they go, okay, here's a support contract.
It's like, what keeps Forth alive? The customers.
Yeah.
It's still there, but yes, you gotta hope that somebody's buying something. Right. It's just the customers that are asking for support.
Yeah, that's what this is. But the nice thing about it, it's a preemptive real-time operating system.
Is it safe?
I think it is. Or is that free RTOS? See, the problem with free RTOS, when I looked at it, it's thread local storage. You have to programmatically do it. I don't want to dick with it. Just be able to just have, when there's a task switch, it does all that stuff automatically. Really? Okay, nope, there are no pictures, but so I looked at this and I thought, this looks pretty good. But also, the nice thing about it is if I can get this thing to run virtually using QEMU, then I can do all my development in that environment, get it to work, and then when I go to an actual target, then I can just take this code, bring it over, and the only thing I have to make sure is that the drivers are all up to date, because I'm going to a different architecture. And I thought, well, that'd be real cool. Oh, guess what? It's got a VNC server. All these things. Oh my God.
It sounds like they're close enough to Unix.
Yes.
You just pull the drivers up.
Yes.
Well, I think this whole thing started out because NX was intended to be, the letters NX was next X. Yeah, it's supposed to be a superset of X11 where it's more compact, it's not responsive and stuff. And then people just started contributing it, and the next thing you know, you got a kernel, you got memory management, device drivers.
Yeah.
You've got customers.
Yes.
And they just keep on just because of the legacy support.
Exactly. Oh, and the other thing that I would like to try to do is be able to implement NUTX, take it from C, translate it to fourth. Yeah, yeah, that's pretty ambitious. Yes, yes. So that everything is in fourth, but it's preemptive. You know.
There are less expensive and less time-consuming punishments available.
Well, it depends on the size of your cerebrum and the number of folds in it, and how much grief you want to put up with. You know. And also depending on the current level of brass in your engineering testicles. So anyway.
We've all got dreams.
Oh yes, 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 yes. So you know, I just would like to be able to do that, because then it makes your, say if it's a USB device, it makes the firmware inside a little more harder to re-engineer, to reverse engineer. Right? Because it's not C, because that has a certain signature to it. You know, and
But that's the thing about it, Tyler.
yes, more security, that's what I'm saying, because how many fourth programmers are out there?
And we're dying.
Yes, we're dying off. But hopefully, you know, guys like Andreas back there giggling. The next generation, yeah, yes, yes. You know, it's you guys that, you know, haven't got aren't long in the tooth like us paleo flatulent engineers. So anyway, this is what I want to do. This is what I'm looking at, and I'm going, oh. So all I have to do really is get on the forums, and I haven't had it because I'm at that age in my life where I'm too young to retire, and apparently a lot of people think I'm too old to employ.
It's real tough.
Yeah, and I'm hoping that those H-1B visas get deported. Oh yes, yes, yes. Yes, 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 yes. And if anybody has had, yeah, if anybody's had the thing of actually trying to look for work, noticing that you're getting phone calls from people who are from India. Yeah. And you'll find it's very, very hard to talk to them because, well, you know, it's their English. Anyway, what I've been up to.
That's the problem. They're speaking English and you speak American.
Oh, God. Yes. Okay, so you're welcome. I can shut this puppy down and, oh, God. Okay.
Glad to see that it's a lot more than just a window.
Oh, it is a lot. That's the thing. That's what I like about it, you know.
The next meeting, June. And Andrea's gonna give us a book report.
Next
Cool.
month will be the Post Maker Fair workshop.
Okay. And then we're done.
Who seems to have vanished is going to give a
Gone already.
haiku update in June.
Okay. And we'll see you all next month. Bye-bye.